nicest land acknowledgement I've ever heard. That was really nice and educational as well. So yeah, hey everybody. It's really fun to be here and also to see maybe the best turnout for a colloquium that I've seen in a long time. So yeah, thanks a lot for the enthusiasm and for being here. So indeed, I want to tell you about an experiment that I'm working on now based at TRIUMF, which is looking for a new particle. So as always with the colloquium, let's start at the very beginning and start by talking about what we know about particle physics. Sorry, I'm going to be moving around a little here while I figure out the best angle for gesturing and seeing things. Maybe we'll just try here. OK, what we know about particle physics. You've probably seen this illustration before. This is the standard model of particle physics, and it encapsulates all of the particles that we have observed and know to exist so far, as well as which are nicely described by the mathematical model that we would refer to as the standard model. So these are divided into 4 categories on the right-hand side here. We have quarks in red, which experience strong and electroweak interactions. Leptons in green, these have only electroweak interactions. Bosons in blue, these are the force carriers, so mediate interactions between leptons and quarks and amongst them. And finally in black in the center, the Higgs boson, which is responsible for electroweak symmetry breaking, and which, as you have probably all encountered, was first observed at CERN in 2012 and was the last predicted piece of the standard model that we had not yet actually seen in the lab. So especially when you draw it in a circle with the Higgs in the middle, it looks very nice, but it's very reasonable to then ask ourselves, is this picture actually complete? Is that the entirety of the particle content of the universe? And to start answering that question, let's take a step back and ask what we know about the rest of the universe. Well, one thing we know is how gravity works. So we can look at a galaxy and predict how stars should move based on their gravitational interactions with all of the rest of the mass that we can see. This is almost certainly too much of an introductory level slide for anybody at an institute with so much observational astronomy and dark matter expertise, but we'll go through it all the same. So if stars were the only matter in the universe, and in the galaxies that they make up, then the velocity curve as a function of radius from the center of the galaxy would look something like this. But what we see in reality is that stars' velocity follows a curve a lot more like this one. So this suggests the presence of additional invisible mass in the galaxies, which is affecting how stars move, which is what we would refer to as dark matter. There's other cosmological evidence for dark matter as well. I put this up just because it's, I think, to me, the most entertaining of the pieces of evidence and one of the most fun to look at, which is gravitational lensing due to dark matter. So what we see here, the sort of ring of stretched and reflected looking galaxies are from a single galaxy in the distance in the back there, whose light is being bent by dark matter in between us and it, such that we see these essentially optical illusions, a sort of reflection of the galaxy visible in space around it like this. In total, using this kind of evidence and what we can put together from looking at space, we believe that there's more dark matter than there is visible matter in the universe. But this kind of cosmological evidence is the only positive confirmation of dark matter that we currently have. We see it in space all the time, but we don't see it in particle physics experiments, terrestrial experiments, and so on to date. So what do we actually know about dark matter based on these observations? Well, there's a few things that we do know, right? We know it has a long lifetime because we don't see any evidence of it decaying. We know that it has no electromagnetic charge. That's what makes it dark. If it had an electromagnetic charge, it would interact with photons and we would be able to see them. And we know that it has a specific density. And when I say that, what I mean is that we can use these cosmological observations to measure how much dark matter there is in the universe, essentially per unit volume, which gives us a density of it. This is one of the images that leads to that. I'm not actually sure if I'm laser pointing effectively, but the thing on the left-hand side here is a map based on gravitational lensing of CMB photons, giving you a distribution of dark matter in the universe. And we can use this kind of thing to work out what the overall density of it is. But there's still a lot of stuff that we can't know about it from the observations that we have so far. One thing we don't know about it is its mass. And we really don't know this over a pretty staggering range of possibilities. The mass of whatever these particles are making up the dark matter density could be anything on a sort of gigantic scale here, where I'm highlighting what we would think of as LHC energies, or roughly what we would probe at accelerators, kind of in this nice section in the middle here. But we also don't know whether dark matter is a particle. It's pretty reasonable, I think, to assume that it would be, and most of the models that I see at this point assume that it is. Anyways, most things are particles in the universe, so a reasonable bet. But assuming that it is, we also don't know if or how it connects to the standard model. That doesn't stop us from looking for it with experiments. So this is also a diagram that you may have seen before, and I think it really nicely illustrates all of the different ways that you can set about looking for dark matter experimentally. All that we're positing in this image here is that there's some kind of interaction, which I'm currently illustrating as a blue blob, that connects dark matter to the particles of the standard model. And it doesn't really matter at this point what the blue blob is, but you could still use this to inspire a couple of different ways to try to do a search. So the first thing you can do is by reading the diagram from the top to the bottom. And if you do this, what you're seeing is two dark matter particles coming together, annihilating, and creating standard model particles. And searches for this kind of process are what is done by indirect detection experiments. You can also read this from left to right. And if you do that, what you see is a dark matter particle coming in, scattering off of a standard model particle, and the two of them will recoil. So this is something you can look for by trying to observe that standard model particle bouncing back essentially from a dark matter interaction. And this is what we do with direct detection experiments, like the really big liquid noble gas experiments that are searching for dark matter right now. But the third way that you could read this diagram is from the bottom to the top. In this case, you have a couple of standard model particles coming in. They undergo some kind of interaction, and dark matter would come out. And this is the way that we try to search for dark matter at accelerators. So experiments like ATLAS, in which Canada has a big part, are continually doing dark matter searches with this kind of concept in mind. DarkLight is doing something pretty related. This is the experiment we're going to talk about today. And while it's not exactly this diagram, you'll see how it's connected momentarily. So the basic idea here is that if there is some interaction between the dark sector and the standard model, and the energy scale for that interaction isn't too high, then it's possible this is something we could make in the lab. So let's think a bit more about how that interaction is going to work. Let's assume that we have all of our standard model particles over there on the left, everything from the circle from the first slide. And over here on the right, we have dark matter. It could be one particle, it could be a bunch of particles. Doesn't really matter for the purposes of this. What matters is they only talk to each other, and we don't have them interacting directly with the standard model. But if we are going to have that blue blob, if we are going to have some kind of connection here, then there has to be at least one particle that can interact on some level with both sides of this picture. There's various hypotheses, as you'll see, many, for what exactly this kind of interaction could look like, what your dark sector could look like. There is a possibility that some mediator to the dark sector could be a standard model particle whose properties we haven't completely measured yet. So for example, the Higgs, as I mentioned, is fairly new on the timescale of things we have studied, and we haven't measured all of its branching ratios to such a complete degree that we don't know for sure it doesn't have some invisible decays. But it could also be a new particle with Higgs-like or photon-like or Z boson-like couplings, or something else entirely. So if I, an experimentalist, want to look for something like this in the lab, there's two ways I could go about it. I can either look for signs of dark matter production, which as you can imagine is kind of experimentally difficult, or I can try and look for the mediator particle, try and work out what would be actually handling this interaction between us and dark matter. So let's build a very simple model. We're going to go back to the blob, and we're going to ask in a little more detail what it is. And we're going to take one of 1,000 possible answers, but one that you'll see numerous times. We'll make a simplified model by taking the easiest possible answer to this question, and we're just going to put in a line. So we're just going to say we have some new mediator. It has a coupling to the dark sector. It has a coupling to the standard model. It has some mass. That's it. So now we have a model with maybe 4 free parameters, but that is, as it turns out, more than enough. And there are practical consequences for our simplified model here, depending on how strong we assume the couplings are at these two vertices and how they scale. So this model really is simple. There are many and many more complex possibilities, but simple models like this are actually very useful to give us a context for thinking about our experimental reach and for helping us to plan out what it is that we can actually do. There's a nice thing about this model too, which is that this new mediator we've drawn in here behaves like the standard model bosons. It has the same kinds of S-channel couplings as a photon or a Z. You can basically just throw another one in there and say, let's say we've got something very similar. So this classic simple model for a dark sector mediator is a dark photon, which is symbolized A prime most of the time and will be throughout this talk. So aside here, because I know we're not all particle physicists in the room, and I'm going to be showing some of these diagrams, I want to just introduce how to read a Feynman diagram, which is what these guys are. Like the blob diagram, you could read this in basically any direction, but traditionally, or in sort of a accepted fashion, we would usually assume the time flows from left to right in these diagrams. So that means that the stuff on the left-hand side of the diagram is your initial state. This is what was inside of your protons or your electron beam or the target that you hit. This is what you start with. Things in the middle of the diagram, these are your intermediate particles that take part in the interaction. And things on the right-hand side are the final products, what ends up in your lab or in your detector. So whatever comes out on the right-hand side is what we actually end up seeing. So with that in mind, let's go and draw a few somewhat more detailed diagrams here and start thinking about how we could look for a simplified model like the one we were just looking at. A new boson plus dark matter. So I mentioned that there are two ways you can do this. Let's look at them in a bit more detail. For new bosons that parallel the standard model photon in Z, but could mediate to the dark sector, there's two most basic processes, or sort of tree level, what is going to happen at a collider. The first is this right here. So we've got two standard model particles in, make an A prime, dark matter goes out. One thing this requires is that we have to have a situation where the mass of our dark photon is at least twice the mass of dark matter. Otherwise, you're not going to have this decay happening in the lab. But the interesting thing about this is what the signal would look like in your detector. We don't detect dark matter, right? It doesn't interact with us other than potentially through these very small processes that give us this tunnel to it. So this dark matter, if we make it, will just disappear. We won't see it at all in our experiment. Now that in and of itself is a signal. That is something that we can measure, that we can reconstruct, and that we can say we saw something interesting. But it's pretty tricky. The other thing we could have is some process like this. We're using standard model particles to make our new mediator. It could just decay back to standard model particles. We know we have that vertex. We put that vertex in our model. And in that case, we could measure those. And the signal that we would get out in this situation is what we would call a resonance. So we would find that there are pairs of particles corresponding to the mass of our A prime coming out in the lab that we can record and measure, and that would tell us something about our new boson. So as a little example, we're going to walk through, and you'll see why in a moment, dilepton signatures. So if I was to run an experiment, and I'm going to make a graph here of the invariant mass of two 4 vectors for 2 muons I measure in the lab, and how often I see it. Then for standard model processes alone, I'll get a different thing than signal. If this is our signal, and it's going to look like this, then when I take those 2 muons coming out, and I make their invariant mass, I'm going to get a bump, and the masses of the bump is going to align with the mass of my A prime particle. Now, there's a lot of ways you could have this with just background. This is a fairly obvious example here. We're just going to have a standard model photon. Same thing, 2 muons come out. But if I accumulate across a large number of events with this, I'm just going to get essentially a smooth distribution with no particular features in it. It's going to be more or less a random mass, but falling off as you go to higher values. So what we can see here is that there's a very visible bump. The signal sticks up on top of the background, and you can just go in there algorithmically and pick it out and say, we saw something interesting. So this is how a resonance search would go about looking for a new boson that could give you this kind of a signature. So this is a bit of a more cumbersome slide here, but I'm throwing it in because I'm going to talk a lot in this talk about limits, like experimental limits, or what it means when we say that something is excluded. So I want to take a moment and explain what that means. When we say that we are setting a limit on some model, what we mean is we're making a tangible statement about which signals are excluded or still permitted by a measurement that we made, right? There's a big difference between not seeing something and demonstrating that the something wasn't there. And it's that, the question of what have we shown wasn't there, that underlies the concept of exclusion limits. So as an example, I'm putting up a resonance search result in actual data from the ATLAS experiment up here. What you can see is those pairs of muons measured in data are the black points here. The red is the prediction for what the standard model background should look like. In dotted lines here are examples of what resonance signals could look like on top of that. And the ratio on the bottom shows you that the data and the background agree really well. So we didn't see any new physics, but how much can we quantify that? What we can do is we can take a slice of the data and background in a region like this and essentially calculate statistically how much signal could be hiding in the data there before we would have had to see it. Compare that to the strength of a signal like this bump on top here, and it will tell us, could that signal be hiding in there, or would we for sure have excluded it? This way we can map out by signal mass and by signal height what is excluded and what is not excluded, and turn that into plots. So I'm throwing up a plot here as an example. This is one from ATLAS. Obviously there's a million things going on in this plot, so don't worry about most of them. Really ignore the right-hand side. The main thing here is that everything colored in is excluded using this method for the set of signals we're interpreting for. So what we have here on the x-axis, this is the mass of a heavy boson, something we might be looking for, like we were just talking about our mediator search. On the y-axis, this is the mass of a dark matter particle. So we've again got our simplified model here, a dark matter particle, a new boson, and some couplings. This line along here is that line where you have mass of your dark boson equals 2 times the mass of your dark matter. So what you can see is that below that line, we have a lot of power from what we would call missing energy signals. Everything in yellow here is looking for that boson decaying to dark matter, and that gives us a lot of strength underneath the line. But everything going up all the way to the top, these are signals from resonance searches. Your resonance search doesn't really care what the mass of your dark matter is, because there's no dark matter in that diagram. So you're more or less independent, and you can just kind of set a limit that goes completely vertically there. This said, what I really want to emphasize with this plot is that the exclusion limits we're showing here are only valid in this particular model and in these particular couplings. And if we change the couplings, that is the strength of the interactions at the vertices in our simplified model, we get a completely different picture. So here I have turned down the couplings to quarks and turned up the couplings to leptons. Completely different strength. This green thing appeared, that wasn't here before. That's dilepton. And if I turn down some of those couplings to smaller values, you can see that we start to eat away at the space we would consider covered, and we now have these huge gaps where we would say that we don't have any kind of strength at all. And in fact here, the resonance searches lose their power, and we're getting all of our search in that bottom corner just from the missing energy searches. So what I'm trying to illustrate with this is that the limits are very helpful for showing us what we can and can't probe experimentally, but that statement is also very dependent on the couplings that we pick and the model that we pick to frame them in. That's the first bullet point here. The second thing, though, as you can see, resonance searches are useful, and they are a very useful way to look for these mediators and something that is frequently done for these kinds of searches. So that is what we will be doing today. I want to talk now about the current experimental context for this stuff. I've just shown you how we can look for dark bosons in a vague sense. How do we actually put that onto a plot across experiments and say, we're doing this practically speaking in the lab? Here we have an x-axis with mass of a new dark boson everywhere from MeV up to TeV. So we're just cramming our orders of magnitude on here. Y-axis is strength of coupling. So higher up is stronger coupling to the standard model in this case. Lower down is weaker coupling to the standard model. And generally speaking, the top left-hand corner of this plot is easier to do experimentally. And as you go down to the bottom right, it gets harder. And you can imagine why, right? As you go to higher masses of the mediator you're trying to make, it takes more energy to make them. It's going to be harder to do. Fewer facilities can do it. Happens more rarely. As you move down to smaller couplings, you get a suppressed rate of production for your mediators, a suppressed rate of decay for them. If you get small enough, they're going to travel a measurable distance before they decay, which is also potentially challenging. So we can actually fill these in different ways. The top left-hand corner, like I said, is pretty easy, and we can in fact do it with measurements of the anomalous magnetic moment of the electron. But as you work out this way, it turns out that using electron-positron colliders and fixed target experiments really gives you that nice chunk in the middle there. And then as you go out all the way towards the TeV scale, you need hadron colliders, and to get to the topmost corner here, you need the LHC. As you work down the left-hand side, you get beam dump experiments. And below that, we can actually make some tangible statements using information from supernovas to give us exclusions down in that corner. So let's take a look at some actual limits now. This is relatively recent. I don't think I know of any updates that aren't on there, though I'm not completely sure. What we're looking at here is an exclusion limit plot now. Like the one we saw from Atlas, everything colored in is excluded. And we're looking at what we would call a classic kinetic mixing dark photon model. That's the simplified model that we're using, where visible decays dominate. So most of the time, in this case, we're assuming 100% of the time it's going to decay to standard model particles. And you can see that it follows kind of that diagram we drew on the previous slide. Down here, again, this is just mass of our mediator. Up here is the degree of mixing with the standard model photon, equivalent to coupling. So again, stronger coupling at the top, weaker coupling at the bottom. And it turns out everything on the top there, that whole top chunk, all of that is resonance searches. That's what's been used to do this across different experiments, but it's all the same concept. Those LHC searches are going to be up here somewhere. And then down here we have those beam dumps and supernovas. So this is how that translates into what we saw in the previous plot. Now looking at this, it is, however, reasonable to ask, are we actually finished with low masses? There's sort of this little triangle sneaking up in here where we don't have exclusions. How much do we care about getting up into there? And that really brings along the question of how do you decide where to look for things in general? In such a wide open space where we don't know the mass of what we're looking for, one way to guide us could be looking for other experimental anomalies and using them to point in an interesting direction and say, maybe go over there. So I want to just highlight two anomalies that both kind of hint towards the same region here. The first is muon G minus 2. A lot of you guys have seen this before. This was one of the biggest results of the last couple of years. This is a new measurement of the spin precession of a muon in a magnetic field. This is something that's very, very precisely predicted in the standard model. You can work it out mathematically and you know exactly what you should see, but the measured value is significantly different. So this plot illustrates that here. We've got the standard model over here. Units don't really matter. So the experimental average is over here, and the difference in between those is 4.2 standard deviations, which is big enough to cause some concern. So why exactly this would come about is really an open point. There's, again, a lot of different ways that you could explain this. One of the explanations, which is these days relatively disfavored simply due to the strength of experimental constraints in that area, but which nonetheless is worth talking about in this context, is the possibility that it could be a new particle. So let's say a muon interacting in a magnetic field. Looks like this little diagram here. For additional bosons that you have in the standard model, you're going to have these next order diagrams contributing to the process that you're trying to measure here. So you can imagine that if your standard model prediction is accounting for higher order diagrams, including a photon or a Z, but you have some additional particle too, and that's not in your math, that could cause a separation between what you measure and what you predict. As I say, numerous explanations, but this tends to live, if you were to say that this is a new particle, somewhere in the top left of our previous plot. Now, the other thing that I want to point to is what was called the X17 anomaly. I say was, but technically it's been 5 years, and it's mostly just been radio silence on this. So I'm going to bring it up all the same. This was an experiment looking at the decay of excited beryllium-8 through characteristic energy levels. Essentially, here you would have an excited atom radiating a photon to return to a ground state, and that photon pair-producing an electron-positron pair that you can then measure the opening angle and the momentum. The invariant mass and opening angle of the E plus E minus pair then were found to show a resonant signal. So this is the data that they observed, where black is the data. Dotted line here is the standard model prediction, and you can see the deviation between the two of them would correspond well to a new particle with a mass around 17 MeV. Now, is this a not yet understood detector effect or an unexpected standard model cause? Quite possibly. And there's a couple of papers out explaining how this could be a nuclear effect or various experimental methods or experimental causes that could lead to this observation. Or, as I say, it could be interpreted as being compatible with a new boson. This is something that sits out there on the intriguing list, but not high enough priority to really dedicate a lot of resources to going in and checking something that is most likely unknown, but nonetheless, do we have a good statement on it? And that's the real question here. So if you were to put that anomaly onto the plot that we were looking at before, this dark photon plot, and look at where that would sit, a boson that would account for this, it would sit roughly where the pink line is. And indeed, looking at this, you would tend to say to yourself, that's excluded. But that leads us to the question again of how you define your couplings in your simplified model. The benchmark dark photon in which this plot is made and in which most of our plots are made for experimental limits in this kind of region has its couplings fixed to the standard model photon. Essentially, the way in which these two interrelate is a mixing in between the two, and so the ratio of couplings to quarks to leptons, etc., matches that of the standard model photon in this model, in this plot. But if you move to a situation where you detangle those, you just say we've got some new boson and its couplings are not directly tied to the photon, then you can actually have suppressed couplings to protons. This still gives you something compatible with, in fact, both anomalies, but a very reduced sensitivity from pion-based experiments, which takes out the green there. And so this leads to a situation where you actually have much weaker exclusions. If we were to zoom in on that region, zoom in such that the little pink line from before now becomes the big purple line on here, this is what it looks like once you get rid of constraints from pion experiments. So here, gray is what would be excluded by lepton-based experiments. Green is the band preferred by G-2. And in fact, this should move down a little bit because I think this line has not been updated with the 2021 result. So we really need to remake that, and we would see it move down a little. This is what would be compatible with the X17 anomaly. And the white is just open space. So it would be worth probing this space. It's a visible final state. That's what we've been looking at here, with pretty high coupling. We're actually pretty high up on that x-axis. So we should use a resonance signature. And we have essentially constructed a model with suppressed pion coupling, so we should do it at a lepton accelerator. So we're going to do a dilepton search, and we should do it somewhere with an electron beam. Now, I want to put up this slide because this is a conversation that I have repeatedly. The way that I see this is that we don't actually need to take the atom-key anomaly seriously to see the purpose of probing this region, right? It is an accessible, uncovered phase space with some overlap with existing anomalies. Regardless of the possibility of finding something, we'd be remiss not to take a look. So in order to have the best complementarity to the existing and planned results that are in that region, this is something that we should do at a lepton machine. And that brings us to the DarkLight experiment. We know we're doing basically really low mass dilepton resonances. So how are we going to do this? Fixed target experiment is a nice straightforward way to go. Recall that electrons radiate photons when interacting with materials. So we're going to send an electron into a target, in this case a 1 micron tantalum foil, and interacting in the field of that nucleus will radiate either a photon or a new boson if it happens to be in the energy range. That can then decay and give us an electron-positron pair, which we could measure with an experiment. All we need at this point is an electron beam, and we're good to go. Let's briefly show, before I move on to that electron beam, what the experiment would look like that we could do this with. This is a very preliminary design, and I forgot to go and draw in here large enough labels so you can actually see the dimensions on this. But this is about 1.5 meters in this dimension and about 1 meter in that dimension and about this high off the ground. It's very small. This is convenient because you can put it in a lot of places and because it's very cheap to make. What we have in general here is a spot for an electron beam to come in through basically that little porthole on the side of the target chamber. We have a target chamber right here with removable targets on a little ladder so we can take them in and out of the beamline. We have a couple of dipole magnets here. One of them will select positrons coming out of the central region there, and one of them will select electrons. On top of that, we're going to throw a couple of tracking detectors, and on top of that, some trigger detectors. So we can take a look at all of those things in more detail momentarily. What we're actually trying to do with the detector is pick up this electron and positron. There's obviously this electron here too that has essentially taken part in our interaction and just scattered on its way through the target. We don't really care about that guy. So what we're going to do is try and optimize to pick up these two here so that we can reconstruct our A prime. Now the angles and kinematics for these are pretty predictable. That's easy simulation, easy kinematics to do. So what we're going to do is optimize where we end up putting those spectrometer arms to give us the best signal to background ratio based on a target mass for an A prime and the energy of the beam. We then essentially select with the experiment for coincidence. So what we want is a situation where we measure an electron on one side and a positron on the other side simultaneously. Then we're going to reconstruct the invariant mass and do a resonance search, just a bump hunt. This brings me finally at last to the electron beam and where we're going to get it. So this is the TRIUMF accelerator complex. I think probably a number of people here have been to TRIUMF before. If you haven't, it's fun. I hope you get a chance to go. In green is our existing accelerator setup. This here is the cyclotron for which the lab is best known and the various beamlines that feed off of that. Here in red, this is all of the elements that make up the aerial project, which is under ongoing construction at TRIUMF and is going to be our new big flagship thing. Aerial is still very much in progress. It is under construction at the moment, but the bit that is completed so far is that. And luckily, that is exactly what we need. That is a nice electron linear accelerator. So this is what it looks like in a little bit more detail. Up here, we have an electron gun that sends electrons into the beamline. Over here, we have a couple of cryomodules containing radio frequency cavities. So this is what actually accelerates the electrons. So basically, from here on down, we have electrons of 30 MeV energy. As you know, 30 MeV is not very high energy, but it is sufficient for what we're trying to do. After that point, eventually, we'll have a beamline that takes the beam away to aerial. Right now, it just goes left and goes into that beam dump over there. And that's it. So that is an opportunity to put something else in there instead. And so far, we've already installed our first beam test setup right around here in the accelerator. So I wanted to show it to you in a little bit more real life. This is a picture of the E-hull. This is before we put the target tests in place because we had to move some concrete blocks in there that kind of blocked the view. So this older picture is a little bit nicer. But you can see it right here. This is actually the beamline. It's about yay high off the ground. And just various supports, magnets and so on, surrounding it, various diagnostics. This is where we went and put the target chamber, which looks like this. This is not the same target chamber that we would use for the eventual experiment, but it let us do some preliminary tests and measurements of the background by popping some foils in there and seeing what happened. And those first tests we did just about 2 months ago, I guess. And this is the best image I was able to get of it to show you. But this is actually looking into one of the little view portholes on that target chamber at where the electron beam is passing through a beryllium oxide screen, a little scintillating screen that we have to let us find the beam and check how whether it's centered and what the size of the beam spot looks like. So this little bright dot that you can see up here is our beam on the scintillating window. And if I go back and forth, let's see if it's too dark for this. Can you see all those little moving speckles? Yeah, all the little moving speckles are essentially the radiation coming out of this and striking the webcam. So it luckily didn't die after a couple of days in this condition. I don't know how long it'll last, but you can really see how much additional radiation is being caused by this. And that really brings us to the topic of backgrounds. So when I explained resonance searches before, I pointed out there's a lot of standard model backgrounds, there's a lot of other things going on in your space that will create this smooth surface over which you have to look for a bump. What are they in our case? Well, there's one irreducible background, by which I mean you can't get rid of it, it's just there, you just have to deal with it. And it is the standard model version of the exact Feynman diagram that we're looking for. So this is our signal if you just take out an A prime and put a photon in there. We're for sure going to have to deal with this. Interestingly, though, it's not our dominant background. The dominant background is what happens when we have another electron randomly scattered nearby, and then we pick up this positron and a random electron. The ELINAC is very high power, so every time we have an electron going through our foil, it's not just one. We in fact have about 10 to the 9 electrons going through the foil every time. The chances of one of those scattering and ending up with the right momentum and direction to be picked up by our spectrometer is not zero, unfortunately. So these are the two backgrounds we have to contend with, and trying to keep those as low as possible means, first off, we have to be very careful with our choice of where we put the spectrometers, as we talked about briefly earlier. But second, we also need to have pretty good time resolution. If we want to keep that reducible background low, then we need to make sure that at least it's only those 10 to the 9 electrons we're dealing with, and not some from the next bunch or the previous bunch. And since these bunches are only 1.5 nanoseconds apart, we have to be relatively speedy to be able to do that. Assuming that we do, though, this is a simulation for what we would roughly expect our signal and background to look like. We've put in a pretty large coupling here so that you can see the signal easily by eye, just to make this look nice. But here we would be looking at the background in purple and the signal in green and what the sum of them would look like in blue. So you can see again here we have a nice shape that you can pick out and say, okay, there's a bump, we could see that. And we would be able to observe this if such a signal was in our data. So I'm going to show you a few of the details of the experiment now. Let's take a little look at the spectrometers. So I've said spectrometer a bunch of times, but all I really mean is a dipole magnet, which is shaped such that it focuses incoming particles onto a focal plane, essentially some sort of plane above it here based on their momentum. So particles that come in at our kind of target central momentum end up in the middle of this. Those with lower momentum end up going this way, and higher momentum go out that way. So you can imagine if you have a particle, an electron that's just too slow, it'll kind of go into the central yoke of the magnet, while one that's too fast is just going to go into the back wall. So we're going to put a little window on the back wall so that those just carry on out. Most electrons are actually too fast for this in our background, so that'll help keep things clean for us. And then we have essentially a plus or minus 20% momentum acceptance around what we think we would get from a real signal. And then a little bit of angular acceptance in both directions too, plus or minus 5 vertically and plus or minus 2 degrees the other direction. And that's essentially what we can pick up. It's very limited acceptance, so we have to use it wisely. On top of this, I said we're going to put a couple of tracking detectors at and just above the focal plane so that we can reconstruct tracks on the way through. And what we're using for this is gas electron multipliers. Just a one-slide intro to how these work. It's essentially a detector that amplifies the signal from an electron passing through this and gives us a precise location of where it was so that we can reconstruct a track. So you basically have these planes with conductive surfaces and holes in the middle, and then apply a big voltage across it, and that gives you a strong field in the holes, which can cause an electron avalanche on the way through. So you amplify a signal, and then you can read it out. You can stack multiple of these to get an even stronger signal. And something built like this is roughly what we're using in DarkLight. So we're going to use 2 of these, maybe 3 if we can get away with it, but so far we're planning on 2 on top of each spectrometer arm. And that will be more or less it. And you can see an actual photo of them because these already exist. They were in fact built for the Olympus and Muse experiments, and there's a few left over, and we're collaborating with the institution who made it, so we're going to get ourselves some of those. On top of that, we're going to have trigger detectors. So what the triggers are for is they tell us when to read out the data from the GEMs. The GEMs have decently fast readout, but it's certainly not fast enough that you could read it out on every bunch crossing. That's also just way too much information. So what we want to do is only read it out when we actually have one of those coincidences, an electron on one side and a positron on the other side at the same time. In order to do that, we want something that is quick to read out and has good time resolution to make that measurement. So we're using essentially these little strips of plastic scintillator with these little light guides to get us down to some silicon photomultipliers on the end. Just going to sum the information from that and then do a coincidence between it. At the moment, with the prototypes that we've got a timing resolution of around 400 picoseconds. Remember I said it was a 1.5 nanosecond bunch spacing, so we'd like to get it a little better still. We're making a second prototype now. We'll see how we do with that. But I threw in some photos from the first ones because I think they're kind of fun to see, and it gives, again, an idea of the scale. How this picture of the scintillator is being wrapped. I like it because it's got fingers in it, so you can see they're about this big. So once again, not the biggest experiment in the world, but that's a big part of the fun. And then here's just some of our silicon photomultipliers on one of the PCBs. Okay, moving on to what it will be like when we run the full experiment. We're not going to be able to do the full experiment in the same location as we did these target tests. The reason for that is the ELINAC has a really nice, narrow, well-controlled beam, and as soon as you stick that through a foil, it goes in all directions. If we actually tried to take data at any serious rate at the location up here where our test was, we would lose the entire beam. It wouldn't even make it to the dump. It's just going to go spraying off into the room, which is not a popular decision. So instead, we're going to put it over here in front of the beam dump where we don't have to control it for very far. And here's a photo of what that area actually looks like here. This is the, see the bend in the ELINAC here is this bend right here. And then we've got about 1.5 meters maybe in this location where we can try and squeeze the experiment in. So that's the plan at the moment. I want to put in here just a quick talk on the DarkLight exclusion range, because we've been looking at exclusion plots throughout this talk and talking about what's excluded and what's not excluded. What can we actually do with DarkLight? This is, I don't know why, a different aspect ratio from the last version of this plot that I showed you, but we're looking at the same thing again here. Gray is excluded, green is G-2, and this is the top of that X17 band where it's not excluded. With what we can do at the current accelerator, and running with different target masses, whether we're sort of optimizing those spectrometer properties to be looking at, I think this is 13 GeV or MeV versus 17 MeV, you can see that we get quite different exclusions. There's good overlap with G-2, but basically only where it's already excluded. And we can't reach the 17 MeV interesting region down here at all. So DarkLight at 30 or 31 MeV, which is what we could do right now, is basically a proof of principle experiment for us. It lets us figure out the running environment at the aerial ELINAC, figure out a detector, do a full analysis, know what we're doing. Important stuff, but it doesn't really get this nice white region that we'd like to fill in. If we could run at 55 MeV, we can get this. So DarkLight at 50 or 55 MeV is something that we can do at TRIUMF through upgrades to the accelerator. Again, 50 MeV is not that high. It's just a question of having something that's compatible with the technology here and actually put in place to make this happen. So if we were to run at 50 MeV, this is what that would look like. I'm going back here to the diagram of the ELINAC, and in gray, this is all of the infrastructure that already exists. In colors, I guess, is what we'd like to build. So some of these bits are not super important. The sort of really two fundamental new pieces of infrastructure are right here, a new cryo module, an exact copy of the old one. We're just going to put it just downstream, and that will give us that extra boost to 50 or a little bit more MeV. And then here, this little secondary beam line will come off over here, and we'll have a new beam dump down here, and we'll move the experiment to in front of the new beam dump. This is essentially just fussy stuff to do with what the old beam dump can and can't handle, but this new layout would be one that is much more robust to having the experiment in front of it and that we're less likely to break. So once again, all in favor of not breaking things. In this design, we'll also have the equipment that we need to allow us to send alternating bunches of electrons to aerial and to DarkLight. So essentially, using this little patch of infrastructure right here, we'll have the option to switch every second bunch one way or the other. So one bunch will go up this arm to aerial, the other over to DarkLight, and vice versa. So that way, if aerial comes online while we're still running, we'll be able to run in parallel. But moreover, it means that new experiments will be able to run in the same location after DarkLight ends. DarkLight has a very short time scale. As you can see, it's a short, simple experiment. We're just going to do it. It's going to be done. When it's done, we'll still have a new cryo module. We'll still have a new beam dump. We'll still have an experimental site. We want to be in a position where we can actually use this into the future, and being able to run in parallel to aerial will really help us to support that. So I've just said this is a short timeline. I want to just pop up here what we're actually looking at, what it is that we're trying to do. So you'll see as well on here how quickly things have been moving. This experiment was just approved for beam time at TRIUMF in spring of 2021. Last year around Christmas, we installed the test chamber in the beamline. May of this year, we held a workshop at TRIUMF talking about some of the details of this, as well as some of the potential for what else could be done at the ELINAC in the future, and held our first collaboration meeting. August, we did those first beam on target tests and our first background measurements. I haven't shown you the background measurements today because they're really ugly plots, but it was useful for us to have that. And here we are down here right now. Looking forward into this next winter and into the spring of 2023, we want to bring down and install an existing spectrometer just to give us some more detailed background measurements and really try that out. And by this time next year, looking at our current schedule, we should actually be able to install the full experiment and start running at 30 MeV. Now comes the TBC. If we get given money to upgrade the energy of the ELINAC, which we will find out about next summer, then we can actually have that in place about a year after we get access to the funds, so that we would be in a position then to install and hopefully run at 50 MeV in around 2025. So looking forward past that, finish our data taking, and plan next experiments for that site. Just going to flash up here also, these are all the institutions that are part of our collaboration at the moment. You'll see it's a number of Canadian institutions on here. We've got UBC, St. Mary's, Manitoba, and Winnipeg, in addition to TRIUMF. So a nice little Canadian contingent who are working on this, plus various collaborators in the US. And Mainz is joined to some extent, though I don't know how officially, so they haven't made it in the official collaboration list, but we do have one European on here as well. So this is bringing me to a little bit of a wrap up. I just wanted to put a few slides to try to summarize what it is that I'm trying to say here today. The first one is about the big picture. This is a really nice plot that came out of the SNOMAS process in the US a couple of months ago, which is summarizing the current and future state of dark photon searches in visible final states. So here in gray, we have once again the kinetic mixing dark photon excluded state of the art. In like the colored filled in lines, these are experiments that are moving forward, not existing limits as yet, but projected limits from these experiments. So you can see that there are a number of these in particular that are going to have something interesting to say about the same range that we're looking at, in particular LHCb and most likely Bell2. That's us up there. As you can see, on the context of this whole picture, it's a very small reach. But as we talked about earlier on, it's still an interesting space. And it's still an interesting space to do in a purely leptonic way. It's complementary to LHCb and Bell2 on account of that, because both of those would be doing searches in this region primarily through looking for meson decays, which is a different production method than we would be looking at and is complementary information for us. And we're on a competitive timeline. This also tells me something about the role of small experiments in particle physics. The scope of DarkLight, as we just saw on the previous slide, is very limited, but so is our budget and so is our timescale. In a field that's really dominated by large, long-term experiments, I think it's pretty cool that there is a small, useful thing that can be done by a small, focused collaboration. And so to show what I mean visually, I wanted to put up here, this is my old experiment. This is Atlas that I used to be on. And this diagram has some little people for scale, little people over here, little people down here. This is DarkLight. So I think that there's a lot still to be done by little experiments, and it's fun to have a chance to do it. The other thing that I think about when I think about this stuff is the role of our benchmarks when we talk about exclusions. This plot I just showed is very useful, and that's why I showed it. That's why it was made for SNOMAS. But having specific benchmarks that are the only way we think about things can also be a bit of a trap, you know? Why is this the only model that we think about when we think about visible decays of new particles at low masses? We run into similar challenges, I think, at the LHC all the time, right? I used to do a lot of SUSY searches. And you back yourself into some weird corners when you go and put out their exclusion limit plots that say, oh, we've excluded all gluinos up to like 3 TeV or something, when in fact that's a very model-dependent statement, and it really depends on exactly what situation you've constructed. There are a lot of cases where that just isn't the case. To me, the current anomalies that we're talking about are interesting, not necessarily for what they are themselves, but because they make us actually look beyond these standard contexts and go, oh shoot, did we really never look there with just electrons? Like, why not? Maybe we should do that. So having the opportunity to actually find our overlooked holes is a really useful outcome of these kinds of anomalies that we see today. And then another final thought, sort of unrelated to those, but this is more from the lab's perspective, is that TRIUMF is excited that DarkLight will help us transform the E-Hall into a user facility. So the ELINAC is very low energy, 30 to ideally 50, fingers crossed, MeV, but very high intensity, up to 10 milliamps. So this is a very high power device, just at fairly low energy. This means it could be a really interesting site to host a low energy electron physics program. So possibilities for what could be done with that include hadron structure studies, QED studies, potentially other dark sector searches. We're really just starting to think about it, but if there are people here who like low energy electrons, start thinking, and there will be ideally a spot to do that in about 5 years' time. So that brings me to my last slide, which is just to summarize. There's really continual progress in the area of dark photon searches and new physics searches from ongoing and new and future experiments, including DarkLight. There's continuing work as well that I don't want to overlook from our theorist colleagues, which is really critical for us in making sure that we understand what we're doing and what we should be doing and where we have coverage and don't. Small experiments do still have a part to play, and depending on who you talk to, potentially a growing one in the upcoming years. And the next few years are going to see a lot of new data, so there's a lot for us to look forward to. And I just wanted to end with a tiny plug that we're hiring a postdoc. So if any of you think this sounds like fun, you could see a whole experiment start to finish. Come join. That's all. Thank you.